let's take a look at example number 2. Here I'm interested in setting up, but not evaluating, an integral which yields the exact surface area of the figure that's obtained when I rotate. Hey, look at this. Again, it's my same curve, y equals x cubed, on the same range of x's, but I'm going to rotate it around the y-axis. Okay, so I'm going to go ahead here and just quickly sketch out what this 3D solid is going to look like. And to do that, I should probably switch colors first. So I'm going to go ahead here and say that I know that my curve looks something like this, and when I rotate it around my y-axis, I get my mirror image duplicate over here. I play a game of connect the dots. Again, just trying to get a rough picture so I can get a loose idea of what's going on. And I can play connect the dots down here. I don't really need to draw too much on this because, again, I'm just interested in trying to determine ultimately the outer surface area of this. That is, like, how much paint would it take to paint the outside of the figure here. So if I have this, I can now go ahead and start to see which way my frustums are generally stacking. And it seems like my frustums here would be kind of stacking in this vertical direction. And so because of that, I know this is going to probably be a dy problem that I should start with by default. So I'm going to start immediately by identifying that I'm going to be instead working with the function of x is equal to y to the 1/3. And my range on y values here, like we saw in the last video, goes from 1 to 8. Remember, that's my lowest y up to my highest y. So I need to go ahead and check to make sure my conditions are met here. So I'll start by saying we see that x equals y to the 1/3 is indeed non-negative on the interval from 1 to 8, right? I only get positive outputs from this on the interval from 1 to 8, so that's good. Also, x prime, which is 1/3 y to the negative 2/3, is definitely going to be continuous on the interval from 1 to 8. Notice again that if I was to rewrite this, my y to the 2/3 power could be shifted to the denominator and made positive. And then the only time where this would be discontinuous is at 0. And since 0 is not a part of our interval, we know we have a nice continuous function there. So because of this, I know I can go ahead and I can set up my surface area. But again, since my frustums are stacking vertically, this will be by default a dy question. I'll start by setting up my arc length portion at the back, which is 1 plus my derivative squared. At the front, I know I'm going to have 2 pi, and then, wait, let me also fill in my bounds here. Bounds go from 1 to 8. I'm also then going to have this 2 pi, and then multiplied. Remember, this piece is supposed to measure the radius. Well, if I look here at the radius at one of my frustum, one of the sides of the frustum, I can tell that's going to be given by my actual function, right? It's like an x-coordinate minus 0. So that x-coordinate is given by my y to the 1/3. That's how I would measure that length. And so this is my default setup. Of course, this isn't the only way that I could set this up. I could, if I wanted to, change this over to be a dx integral. That doesn't mean I'm changing the picture, just means I'm changing the way how pieces are going to be measured. We can start by changing the arc length piece. That would be 1 plus a new derivative squared, but I'd have to work with my original function up here, y equals. Notice the derivative of that is 3x squared. On the outside then, my bounds would have to go from 1 to 2, since those are the range on x. And then notice that here, I would have to replace again my y to the 1/3. And what is y to the 1/3 the same as? Well, it's the same as x. So I would just replace that with a single x. And boom, we've completely transformed our integral with respect to y into an integral with respect to x. Now again, one of these integrals might be easier to compute than another. In fact, I might actually pose that maybe the first integral here is going to be a bit easier to work with. Although, since we weren't asked to evaluate either of these integrals, we're not going to worry about it here in this video. But hopefully you can see with both of these examples, that is the one from the last video and this video, being able to set up these integrals in 2 different ways is very valuable. And I have to understand how to do that. Which way is like the default way to set it up based on which way the frustum stack, and I have to understand how each of these pieces is being measured. Also note that on each of these problems, I have to check the conditions. That's not an option. That means that when you do a problem on an assignment or when you do it for an exam, you have to actually write out those checks. If you don't write them, but you just mentally do them, I won't know that you did them. And your job is to show me work to demonstrate that you understand how to do the problem. You're trying to convince me of the solution. And so it's important that you show those individual steps.